The following reaction reaction takes place. The following reaction takes place, and you have OH minus being added to your weak acetic acid, and what that gives you is what? Water plus what? Your acetate. So OH is eating up or locked, so it can't float around freely in solution. Okay, thus in the above thus in the above reaction, the OH minus is locked or eating up, so it cannot float around, it cannot float around freely in solution to change the pH, cannot float around freely in solution to change the pH. Cannot float around freely in solution to change the pH. Okay, so that's like scenario one. So I want to look at another scenario. I do this in another color. Then it says, supposing I introduce the hydrogen ion concentration in the solution, the following reaction what takes place. So suppose I introduce H plus ion, which represents the acid in the solution. H plus ion, supposing I introduce H plus ion in the solution, of course in the solution of what? Weak acid, in the solution of a weak acid, the following reaction will take place. The following reaction takes place. Following reaction takes place. So what you have is your H plus now is introduced to your acetate that is in solution, and that forms what? Back your weak acetic acid. Okay, thus in the above reaction, as seen in the above reaction, H plus is trapped by ACO minus, and it cannot float freely and change the pH. So it cannot float freely to change and change the pH cannot flow freely and change the pH. Great. So that's basically how the buffer system works. So that in what so that is what a buffer does. It has the acid, it has the base. Whether I add OH minus or OH plus, it is in either case it will react with one of them to lock it in or eat it up. Eat it up. So it is not floating freely to change the pH. That is exactly how buffer works. So recall that when the concentration of acid and conjugate base are equal, that is an what ideal buffer that has the highest buffer capacity. Okay, so recall that. Recall. Let me do this in another color. Recall that when the concentration of a weak acid recall that when the concentration of a weak acid and its conjugate base are equal, that represents an ideal buffer that has the highest ideal buffer that has the highest buffer capacity. That has the highest buffer capacity. That is it. Has the highest buffer capacity. Great. So next we'll be looking at an example of a buffer system. Okay, in the next page. Okay, so note that weak acid and weak basis buffer our cells and what tissues. Important to note, okay, for physiological systems. Okay, acid weak acid and weak basis weak acid and weak basis does what? They buffer our cell system and tissues. They buffer our cell system and tissues. They buffer our cell systems and tissues. So next we want to look at example of a buffer that buffers our cell system and tissues. The example of a buffering system is what? The phosphate buffer system. The phosphate buffer system. So this is the buffer system that operates within the cells. It acts inside the cell. So inside the cell, you want to keep the pH range within 7 to 7.4. Okay, so the the phosphate buffer is perfect for that pH range. Okay, so I take another layer. This is the buffer system. This is the buffer system that operates inside of the cell. Inside of the cell. So because it operates inside of the cell, keeping the pH range between 4 to 7, the phosphate buffer is a perfect form for that because of the following. So inside of the cell, thus keeping the pH range between 7.0 to 7.4, the phosphate buffer is perfect for it. Phosphate buffer is perfect for it. Is perfect for it. So we want to look at the phosphate buffer and the reaction that can take place as follows. So looking at the reaction of the phosphate buffer is shown below. So we have H2PO4 minus, forward reaction, backward reaction, and this donates proton to form HPO4 2 minus. So here this is acting as the acid. This is acting as the acid, and this is acting as what? The conjugate base. Again, this is the proton donor. This is the proton donor, and this is the proton acceptor. This is the proton donor, and this is the proton acceptor. And this pH operates as a pKa of what? 6.86. That's the pKa of a phosphate buffer. So because it operates at this pKa, the buffering region will give a range. Buffering region will give a range of pKa plus minus 1, and that gives you a range of 5.86 to what? 7.86. 5.86 to what? 7.86. This range, as we can see, we do that in red. This range right here, as we can see, is perfect for cell buffering. Is what? Perfect for cell buffer. It's perfect for cell buffer. So the acid here is the hydrogen phosphate, and the conjugate base is the acid here is the dihydrogen sulfate, and the conjugate base is the hydrogen phosphate. And the relationship is that when one loses a proton, it turns into the acceptor, and when the acceptor gains a proton, it turns into the donor, which is what? The acid. Thus, in the cell, there is some of the donor and some of the what? Acceptor. The pKa is 6.86, and the buffering range is pKa plus minus 1. Thus, the range of the phosphate buffer is what? 5.86 to 7.86, as shown in the calculation. Okay, and this is actually perfect. Why? Because we say the normal pH of the cell is somewhere between 7.4, 7 to 7.4, 7.0 to what? 7.4. And this, of course, implies normal pH range. Normal pH range. So that's why we say it is perfect. This falls within the range of the phosphate buffer, and that is why it is a perfect buffer. And this is why cells use this as a buffer inside the cell. In this case, the equilibrium shifts to the right or left depending on the metabolic processes of the cell. This ends our set of lectures for buffer today, and in our next class set of lectures, we'll begin to look at practical problems and examples that we can use to apply to calculate and solve for titrations and buffer. See you in the next class. Thank you for joining Dr. Elick today for titrations and buffers.